But it would be helpful to do a worked example for a galvanic cell. So let's just go through this one. It's from a 2016 prelim. So we've got a chemical cell setup as shown in the diagram below. Galvanometer registers a reading. So because we can't see a battery, we know that this is the battery or this is the cell. So let's just see what we've got. And my recommendation is before you approach any of the questions that you actually just spend some time looking at your cell and make sure that you've got everything down that you possibly can have. So we've got silver, silver nitrate solution, magnesium, magnesium nitrate solution. So we're probably assuming that our nitrate is going to be a spectate ion, but let's check. Hopefully this will all fit. Yes. Okay. So we've got magnesium. So there's our two nitrates again. There's the nitrogen dioxide, nitrogen monoxide. We don't have those, which tells us that these are not. It's not a full reaction that's taking place. However, we do have both magnesium and a magnesium ion, and we do have silver and a silver ion. We don't have all the full ingredients for the nitrates, which confirms our suspicion that that was a spectate ion. So between these two, our reducing agents, the substance is being oxidized. Magnesium is the beta reducing agent. Between these two ions being reduced, the silver is the beta oxidizing agent, and there is our spontaneous reaction. So that then tells us the magnesium is undergoing oxidation and the silver is undergoing reduction. So what I'd recommend doing then is on here to go through and write it down straight away. So we're going to say, here's our oxidation half reaction. I'm just looking at the table, so I'm going to write my magnesium goes to Mg2 plus 2 electrons, and write down where it was on the table. So there's our magnesium and there's the value that goes with it. So write that down straight away so you don't have to look again. 2,37 volts, and then on the other side we've got our reduction half reaction, which is the silver plus an electron going to, a silver plus an electron going to silver, and that value is plus 0,80 volts. So that's telling us that the silver electrode here is going to be the cathode, which means I'm expecting that to increase in mass, and the magnesium over here is the anode, and I'm expecting that to decrease in mass. So because I've got my electrons flowing away from the anode, so they're losing electrons, it means my electrons are flowing in that direction through to be picked up by the silver. This side's going to be increasing in mass overall, so that's going to increase. This side we're going to have an increase in the magnesium 2+ ion content within the half cell. And this side we're going to have a decrease in the silver ion content because it's been used up. It's going in to be plated onto the electrode. In terms of what this is our salt bridge, and most substances would be okay to go in here. I would probably recommend a substance like potassium nitrate, because potassium ions never form precipitates, nitrate ions never form precipitates. Because we've got silver here, we need to be careful of the halides, because remember, halides will form precipitates with silver ions, so that's something we must just be careful of. And then, one last thing, in terms of this being oxidized, this is the substance being oxidized, which means we can just fill this in. So this is our substance being oxidized, the magnesium, that's why it's the anode, and that means the magnesium itself is the reducing agent. And because this substance, our silver, is the cathode, that's the substance that's been reduced, that means the silver ions are the oxidizing agent. So just be very clear whether it's ions or atoms that you're dealing with. Answer the questions. So the first question, 6.1, is not actually about electrochemistry, but it's worth just mentioning. So consider the aqueous magnesium nitrate solution. So that's this magnesium nitrate solution overall. So it asks you first of all to give the formula of the solute that was used to make the magnesium nitrate solution. So remember, that's the substance that was dissolved in the solvent in order to make the solution. So what did we literally dissolve in overall? And that was magnesium nitrate. So I'm just going to write the answers over here. So that was magnesium nitrate, like that. So that's the formula of the solute that was used to make that overall solution, and name the solvent that was used to make the solution. The solvent is generally going to be water unless they specify that it's something different. And then name the specific type of forces of attraction between the solute and solvent particle in the aqueous solution. So remember, magnesium nitrate's ionic, so it's going to dissociate in water into magnesium ions and nitrate ions, and then get surrounded by those water particles. So the solute is going to be the dissociated magnesium nitrate, the solvent is going to be the water ion, and the water are dipole. So that tells us that it's a ion dipole force. Not so much of a thing in the current syllabus. This was a 2016 paper, but still worth knowing. Okay, so now let's go on to the redox part of the questions. And now you'll see is once we've already covered these, we're actually going to answer these questions really quickly. So name the reducing agent. Again, just pay very close attention to what they're asking. Name the reducing agent in this question. So the reducing agent there is going to be the magnesium overall. Give the equations for the oxidation and reduction half reaction. So there we go. We've already done those. So see those above. All right, write the cell notation. We haven't done this yet, but we can do it straight away. So we're going to go anode, then bridge, then cathode. And while we're on this, I just want to mention the fact that the anode is being written on the right. It's been drawn on the right, but when you do your cell notation, always make sure you put your anode on the left. So this is kind of, you can imagine if I'm setting up on a lab bench and I set the cell up over here, and I've got, if I put the anode on my left and the cathode on my right, but if you're looking from the other side of the bench, it's going to be the other way around, but it's exactly the same cell. There's no difference to it. It's like an organic molecule. You can view it from both sides. So there's nothing wrong with drawing a cell with an anode on the right and the cathode on the left. But when you do cell notation, you always need to make sure that your anode is on the left. Remember the ABC thing. So with our cell notation, anode, bridge, cathode. So the anode is going to be the magnesium. And then single line to go magnesium into solution. So there we go. Magnesium, magnesium 2+. And then we're going to go silver ions and silver solid. So double line for the bridge. Then we go silver ions and silver solid. And then is the following statement true or false? Explanation not required. The electrons flow from the magnesium electrode to the silver electrode in the external circuit. From the magnesium to the silver. We had already predicted that, so yes, that's true. And then state which electrode, silver or magnesium, would decrease in mass as the reaction proceeds. So we know we're looking for our anode. The cathode is always the one that increases in mass, but we also already predicted that. There's our decrease. There's our increase, so it's the anode, so it's the magnesium. And there again, they said just state, so you would just be able to write either if you wrote Mg or magnesium would be fine. And then component Z serves to complete the circuit in this chemical cell. Give the name of component Z. We already spoke about that. That's a salt bridge. And they say component Z performs another vital function. So the first one is to complete the circuit, as we know. Another vital function is to maintain electrical neutrality. Briefly and specifically explain what it does. So they want to know what it does, but they also want you to explain how it does that. So it's going to be to maintain electrical neutrality in the two half cells, and it does this by allowing anions from the salt bridge to flow to the anode half cell and vice versa, something like that. You can see how much time you've got to answer the question. You can obviously want to be as thorough as possible, but without repeating yourself. And then component Z is replaced by one which is narrower and longer than that shown in the diagram. State how each of the following will be affected by this change. Answer only increases, decreases, or no effect. So we're saying component Z, our salt bridge, is narrower and longer. In other words, it's harder for it to do its job. So in other words, the internal resistance is going to increase. You would obviously write out the word increase. And how is that going to affect the EMF? Well, our EMF equation is not going to change at all. We haven't changed the identity of the anode and cathode, and we haven't changed any of the standard conditions. All we've changed is the salt bridge. So therefore, the EMF will have no effect. And then would a potassium chloride solution be a suitable chemical for use in component Z? Our answer here is going to be no. And the reason is because the chloride would form a solid precipitate, just abbreviating, with silver ions, which would clog the salt bridge and prevent the cell from functioning. So that wouldn't be good. So even though your potassium ions are a weak oxidizing agent and your chloride ions are a weak reducing agent. So ordinarily they would have been great. They wouldn't interfere with the reaction at all. But because those chloride ions would react with the silver ions to form a silver chloride precipitate, that would be a bit of a problem for this reaction. And then calculate the EMF generated by the cell under standard conditions. So we're going to go, let me do it this way. So we're going to go E naught cell is equal to E naught cathode minus E naught anode. And this is where it helps that you've already written those values down. Sorry. So there's our cathode and there's our anode. So it's positive 0,80 minus negative 2,37. And that gets us a value of, so we need to just make sure we take that negative into account. So 0.8 minus 2.37. Sorry, I'm just showing all the steps here. And we get that answer 3,17. You see that it's positive, which confirms to us that this is spontaneous. So plus 3,17 volts, and that then confirms that it's spontaneous. Okay.